Hello. Okay, let's get going. This is what I had last week, and I believe on my ball, my sphere here, I had weird wind. I was experiencing the wind. I'll just turn the wind off. Just hit play again. We have ourselves a nice bouncing ball, and I showed, how to do this yourself, instead of relying on the physics engine. So you can check out the previous week's video if you want to see what was going on with that. But what I think I'm going to do now is do a slightly different thing. I'm going to start maybe actually I will save this scene, and then I'll save the scene as and I'm going to show one of my favorite simulations that I like to do. Well, actually, before I do that, let's actually go back a little bit and look about drawing a circle. This is worth looking at, actually. So what I'm going to do is, obviously it's a 3D scene, okay? What I want to do is I want to make the object, the ball, move in a circular path. So the first thing I'm going to do with this is I need to turn off or remove my whatever script, and then I'm going to put this, check if this is in the middle. What is 0, 0, 0? Let's just see 0, 0, and 0. Puts it in there, and then let's make the ball bigger so you can see it more clearly. Maybe 0.5. 0.5, which is fine. And I'm going to get my editor up, and I don't think you can see the editor, can you? So I was trying here to use window capture. Sometimes window capture doesn't work very well. We'll see. Maybe is this? Yeah, you can see my editor. Well, I'm going to put the editor up here and then resize this, I think that works. And I've got them side by side. I've got my screen at high resolution. I don't want to do a kind of whole screen capture. Okay, let's take a look at. Yes, I'm going to create a C# script, and you don't see the menus, do you? I knew there was a reason. There's always a reason. There's a reason for not using window capture, and that's that when I pop up the menus here, you don't see the menus. So I'm going to have to switch. So much for that idea. I'm going to have to switch this to like a full screen capture. I'm going to see if I can do this, because otherwise this isn't going to work. So I regret it every time I try to do that. Display capture. Let's turn off these. I'll be back in a moment. And this is capturing, let's see, properties. And that screen is huge right now, display 1. I don't know, does it work? Can it handle it? It doesn't seem to be too bothered by it, actually. I was expecting the thing to choke, so I'll tell you what I will do. I will keep that there. and then just do I suppose this works, and then I can actually stretch this out, and then, ooh, that's cool. You let me know if that's working for you on there, see, and then I turn on my light capture, and we can proceed from here. Okay. Right, so where was I? What I'm going to do is create a new script, which was this thing, and I'm going to call it circle. And drag that in here. All right. So every time we have an update, I think I want to sort of make this thing move in a circular motion. And if we make it move, we may want to make it move in a circular motion around here. So let's see, if I put this here to the center, I want it to start moving around in a circular motion. So how would you do this? Because there's more than one way of doing this. So here's the way that everybody would immediately do it, kind of in the naive way, if you will. It's the most natural way, in a sense, first way people think about it, but probably not the best. So the first problem is if I want it to sort of start here, that I put the object here and I want it to rotate around the center, then, and let's say that I'm thinking about doing this by using sine and cosine. Why sine and cosine? Because sine and cosine are functions that literally describe the coordinates of points on a circle. That is, in fact, their definition. For some reason, the way this is taught in schools, you tend to forget this. It kind of, that point, I found, tends to get disconnected from everything else, which is a bit of a shame. And then people get confused and don't understand where sine and cosine come from and why they are what they are. Well, they are literally the coordinates of the circle. So actually, I will just demonstrate that first in this way. I'm going to ignore where I place this at the beginning. I'll come back to that because I want to actually... Oh, hi there. Dyscalculic. Okay, glass of ethanol. I have a little bit of ethanol in here. Yeah, just don't focus. The thing is, you just focus on the concepts. This could be fun, yes. So the point here is that I'm going to ignore where I place this and just have it move in a circle in some kind of way. And so for this, I will need to think what am I going to do? I'm going to make it move. I need to track. I need something. I need to track something. I know what dyscalculia is. I was a teacher, you know. I've never experienced dyscalculia. I kind of actually, I don't really know what it is, because you actually really know what it is unless you experience it. But anyway, I digress. So what I want to do is have the angle change over time. So even there are different ways of doing it. I'm going to get into some sort of, a little bit of nitty-gritty of the programming end, the way of thinking about this problem, the way of thinking about drawing a circle. This is not about knowing how to draw a circle. This is about thinking about the way that you can draw a circle. And so if I want to track the current angle, say I want to have over each frame, I want this to move around a little bit, around in a circle every frame, I've got to think about how to step through those stages of drawing a circle. So the natural thing that you think about maybe is to use an angle. And so you sweep the angle. So you start at 0 degrees and you go around 360 degrees and you draw the circle. And even there are two different ways of doing it. So I'm going to go really naive. This is probably the naivest way, all right? And then I'll show how we can make it actually more elegant. So what I'm going to do is create, you say I need an angle. So I create a float. I call it angle. And actually, I should remove this, I'll put it back. At the beginning, we're going to set the angle to 0. I know it would already be 0, but I'm just to emphasize, because this would be initialized to 0, because it's a member of the class. So anyway, but the angle is 0. And then here, what I'm going to do is transform dot position equals new vector 3, and we need an x and a z. I suppose because this is the x and this is the z, the y is coming at the screen. So in the x, I'm going to put the cosine math f dot cosine of my angle. 0, because the height of the ground is going to stay 0, and then math f dot sine of the angle. So this will do that. And then each step I go and I say angle plus equal 1. I may be deliberately making mistakes here. The first mistake is always remember to attach your damn script to the object. It's important because otherwise, so there we go. I've attached my circle script to the circle and I hit play. Now, this isn't quite what we wanted, is it? There's sort of almost like 6 appearing there. So the first question we have is, what did I do wrong? What did I do wrong? Classic problem. Unity, in its infinity wisdom, decides to make life simpler for programmers because they call it a scripting language, probably because they had in mind that non-programmers could script, you see. So what they did was that they made their API work in degrees. Now, this is one of those things that you can say that's nice and that's useful because it means that then people understand degrees, but the disadvantage of it is that you end up with things like this. Because it's very important to understand that mathematicians use radians and not degrees for a very good reason. A radian is basically the distance around a circle of unit 1. If you have a circle which has a radius of 1, then you can measure an angle by measuring the length of the circumference for that particular angle that you want. And that measure of an angle is called the radian, and it has very nice properties. And it's actually a meaningful definition of an angle in the way that 360 is just plopped out of the air. And so the maths libraries, they use radians. So what I need to do is understand that this angle here is in fact in radians and not degrees. And so I'm adding 1 radian every time, and 1 radian is approximately 60 degrees. So what I think I'm going to do here, because I can choose now, I need to choose which unit. You know, and then of course compiler won't really help you if you try to add degrees to radians, which kind of makes a bit of mockery of this obsession with type safety. But what I will do is I will choose to work with radians because I'm going to say we're going to be more math focused here. Like, we shouldn't be afraid of radians, you know. I'll show you one reason why it's very nice to use radians in Desmos. If I get Desmos up here. Everything has a reason. Everything has a reason. There's a reason why mathematicians like radians. The problem is at school we're taught degrees before we're taught radians. So then when radians come along, we just give up. You should teach probably degrees and radians at the same time, and not pretend that you don't, need one of them. But anyway, I digress. What I'm going to do is just plot the sine of x, and look, you get this lovely graph. It's lovely, isn't it? Yeah, that's the sine wave. The cosine of x is another sine wave. It's shifted by 90 degrees. And if you plot cosine of some value t and then sine of the same value t over a range of 0 to 1, you get a bit of a circle, because that is a length of 1. That circumference is a length of 1, because this circle has a radius of 1. So if you want to draw a complete circle, then you need to go from 0 to 2 pi. And you get a circle. Otherwise pi, if you go from 0 to pi, you'll get half a circle. You see, it's all quite elegant. And this is what you get, where t is in radians, not degrees. Hey Pete, how you doing? T is in radians, not degrees. Right, now I'm going to show you why it's, or one of the reasons why it's really nice to use radians, because now I'm going to switch this graphing system, the Desmos, to degrees. What happened there? Oh my God! It's gone! I switched to degrees and the graph is gone! Dear God! Because down with degree. Look, this is a nightmare. This is why mathematicians don't use degrees. Because you try and draw a graph, and you know what you need to do? You need to go over here and change the x-axis to go from, say, minus 3,600 degrees to 3,600, not degrees, but whatever, yes, degrees. We've got it back. But it's not a square graph anymore. Our units are now like crazy. You can see you have to go to 90 to go from here to here. Now, for engineering, there was something called gradients. So in fact, there were 3 ways of measuring angles. You never hear about gradients these days, do you? The calculators have them, or used to, probably don't anymore. But I never used gradients. But the radians, you got that. It goes from 0 to 2 pi to represent 360 degrees, because the circumference of a circle of radius 1 is 2 pi in length. Degrees can go from 0 to 360 for historical reasons. Probably goes back to the Mayan culture. The fact that there's approximately 300 or close to 360 days in a year. But 360, but it's just a number pulled out of the air. And on there you get, as you plot this graph, you can see it crosses here. Now, that's 90 degrees, and then here's 180 degrees, and you see it doesn't line up. So what you can do is you can decide to go with gradients, and gradients makes 90 degrees 100. So in fact, the circle is now 400 angles in a circle instead of 360, and that would have the nice property of this crossing the axis here at exactly 100. But we don't use gradients, and we really don't want to use degrees, because this is just ugly. No, much better to go and switch back to radians. Oh my God, look at that. And then make the graph square again. So anyway, that was a little stuff. So what we're going to do is I'm going to choose radians. This is going to be radians, right? And one of the problems of dealing with angles is always this, is that you get caught out with these things. You forget to convert them and all the rest of it. Now, what this means is this will work fine. I am passing radians into a function that takes radians. I suppose I could create a radian class. You could, it's quite technically possible actually, and then you can have some implicit casting, and anyway, so whatever. We're going to do here with angle plus equal 1, but I really want to go a certain fraction of the circle. I'm tempted to say like 1 degree. Well, let's do 1 degree. To do 1 degree, I would need to take my 1, and in fact there is a function available in Unity. MathF, it's not a function actually, it's a multiplier. If I multiply my 1 by degrees to radians, I think, is this correct? I think it's actually a constant. There we go. So I do it back, and I get an error. Does not contain degrees to radians. I've forgotten what stamp. I don't want to look it up. 2 rad? Yeah, it's 2 rad. Yeah, that was it. Sorry. Degrees 2 rad. It's too radical. And now we hit play, and we'll see what happens. And now, what you've got is a thing moving in a circle. I could draw a bigger circle around it, and it will be moving in a circle, in a circle, in an inner circle. The inner circle, never mind. And what I can do from here is multiply, say, this by 2, and then maybe we will get it moving a bit further out. Oh! I've multiplied one of the axes. I want to multiply the whole thing by 2. Let's do that. Multiply by 2. There we go. And there, it's moving in a circle. And there was much rejoicing, for it was moving in a circle. But there is a lot here to look into, because than you might think. How can we improve this? Well, the first thing is, I just want to show that here we have this variable angle here, and we are adding per frame. So we need to worry about timing, because this is on an update. The update is happening, say, about 60 times a second. So this is not 1 degree per second. This is 1 degree every 60th of a second, or I guess it's 60 degrees per second, which looks about right. Also, we don't know for sure what the update is. So then, of course, you might say, well, let's multiply this by time dot delta time. Now, if we do that, what we are saying is we're taking into account the amount of time that has passed every time the update is called, and it is moving. It's just moving very slowly because it's moving at 1 degree per second. So it's going to take 360 seconds to go around this circle. It's rather slow. So let's pop this up back to 60 degrees per second. And that's it. And you look at this code and you think, okay, cool. But, you know, actually there's more. I don't like this code. I really don't. There's something about it that is a bit kind of messy. I mean, why have I got this, to have this here at all? Just for doing this thing. It's got to move around in a circle. Now, everybody, I've noticed, tends to do it this way. You're measuring time, aren't you? Yeah, well, we've almost made a clock, yeah. But you're measuring time by adding to a variable. Is there a better way? So my question for you is, can we get rid of this variable? Now, my point here is to encourage you to think about a different way of doing this. And you might get for your inspiration from it, dealing with something like shaders and shader toy. You see, with shader programming, generally you can't store state. That is, you can't remember something between one frame and the next. This is set up in such a way that you're tracking the position of the ball on a frame-by-frame basis. You remember where the ball is. There's state variable. Every time you add a bit of time to this to know where you want to put it. But you don't need to. We can get rid of that. And it fascinates me how people don't think about it. Because there are a few problems with this. One of the problems with it is that you get, I mean, it's a small, tiny problem. It probably wouldn't really affect people most of the time, or rarely. But you're adding every frame to this, so you're going to get a little bit of floating point precision issues because you're doing many, many additions over time. Well, we can get rid of that. What we can do is get rid of that, and we can get rid of that for now. We can get rid of the stupid comment because no. Transform position equal new vector angle. Float angle equal time dot time multiplied by 1 minute. Let me just get my units right. This is the amount of time that goes past, which is the time. Yeah, no, it's just the time. You do 60 degrees. Yeah, I think that's correct. That's all I need. And I can get rid of that. Let's try it. It's amazing. See, the thing is this will track for any number of frames, actually. I mean, if I there's this thing that can I block it? Yeah, I can block Unity playing by just clicking on the bar up here. Look. Now, if I hold it down for a long time, in theory, I think that if I leave it too long, there's a maximum amount, and that's because I think the time blocks, which is kind of interesting. How about we use real time since startup? Now it's really, I can hold the bar down, and it doesn't matter how much I hold it down for, it's still going to catch up because there's no state. Because it's literally just measuring time and drawing the circle and measuring the amount of time since level load. It's like, that's cool, I think. So this is an example of using a functional way of drawing a circle. And it's simpler, and there's less that can go wrong. I mean, unless it really matters that you don't want this to move forward when time blocks. If you do, then you just actually use time.time, and then that stops when the Unity realizes that things have been frozen for too long, and it just freezes everything. Looks like it freezes after about a second, something like that. All right, now there's more, because this is fairly simple. But you know what I wanted to do was I wanted to take into account where I start. And so that's a bit of an issue. So what I'm going to do is I'm going to reintroduce the start function, and I'm going to look at the position, transformed opposition of the thing, vector 3p equal transform position, and that is, p is going to be the position that I start at. Now I need an angle, because, yeah, I am representing my rotation in angles, so I need to know what the starting angle is. I really hate using angles, but I'm going to do it for demonstration here. Right, so what I want to know is what angle I need to start the circle drawing at the right place. A secondary point is that I need to know the time that the thing started moving. We can assume that since I'm using time.time, that it starts at 0. But for a more general purpose thing, we might want to be able to reset the position at any time to a particular point. So I'm going to just put that in. It does mean, unfortunately, I need to introduce state, but at least the state variable here is only set at the beginning. It isn't set every frame, as you will see. I'll call it start time. So we do start time equals time.time. So literally, when the thing starts up, I remember what time it started up. It was probably going to be 0 in practice for now. But if I was running it in the game and I set it up so that this was turned on after the level had loaded or then started, it would still work correctly, even though time.time will have moved on. It would have started at something other than 0. So I'm going to do it. So I've got my position, but I do need to understand the angle. Again, there are different ways that we could do this. So I'm going to just actually have a starting angle as well. Although you could figure out the start time that created the angle, and then you would get rid of this variable as well. But I'm going to put this in. So what I'm going to do is call this start angle. Because the purpose of this is really to, as I say, is not to demonstrate particular programming practices, but to help with the understanding of the mathematics and problem solving with it. So what I'm going to do is say that the start angle needs to equal something. And what? Well, I know the position. I can get the x and z coordinates of my ball. I want to know what this angle is. And so there's this great function called math f a tan 2. I can't remember if it has a capital T or not. We'll find out. And then you pass into it the x and y coordinates of the particular point for which you want to calculate an angle. So this, in this case, would be the coordinates of my ball, because it's relative to the origin. It's 0 here, relative to the origin. So what you do, of course, as you think about the a tan 2, is you very naturally go in and do the following. P, that's my position, dot x, p dot z, which is the z really being the y, because I have flipped the space around, okay? Because my y on the screen is my z. So you do that. And then I have my start angle. And yes, do bear in mind that I may be deliberately making mistakes, because I'm demonstrating very common pitfalls. So this is a very common one that's about to happen. So then what I do is I take that start angle and then I go here and I put my angle, my current angle, equal to the start angle. Take the current time, subtract from it the start time, multiply it by 60, which is the speed in degrees per second, and there's my degrees to radians, because angle is going to be in radians, and then I pass that in. to my function. Does that all make sense? You think, yeah, that makes sense. So then what I do is I try it. Hang on, you say. Couple of problems. One is I'm not taking into account the distance of the circle from the center. So it's actually, I'm further away than 2 units, because currently I'm at 2 units here. I'm further away than 2 units from the center. So it's going to pop in. Okay, all right, well, I'll deal with that in a minute. Maybe I need to remember the distance. Yeah, well, let's not remember the distance just yet. And then the other thing that's slightly annoying me, actually, if I hit play, if I hit pause here, and then I hit play, I can oh, that's wrong. The angle has changed. That is not the correct angle. I said I wanted it to start at the right angle, and I've gone and used the A2 tan 2 function, which Dino assured me would work, and look. So what you've got now is a problem that something is wrong with the maths. So you have a choice. Unfortunately, a very popular choice is to just fiddle around with stuff until you think it kind of works. Another popular choice is to spend a day pulling your hair out. Rise over run. No, never run over rise. Rise over run. You're absolutely right. I thought you were making some kind of really weird joke, but in fact, Blayman there you can see in the chat, there he goes, rise over run, is a clue, is a big clue as to what the thing is. I remember I had it was an ex-colleague, teacher of mine, who was stuck once, and eventually figured out this particular problem, and was cursing at it. But in fact, there is a reason why this problem happens and why this is, and it's kind of why mathematics needs programming. Anyway, you'll see that in a minute, but I digress, because I'm looking, because basically it doesn't work, because it needs to start at the right. So here, I'm going to show you techniques I use for debugging this kind of horrible thing, because it is actually, you need a specific skill set, really, for debugging something that moves. Everybody understands debugging static stuff, and for that you can use a debugger. And people feel quite confident about that, but believe it or not, that is nothing compared with debugging something that moves. Debugging something that moves is like trying to shoot a moving target. It's quite difficult. This isn't so difficult, this little example, but it shows the kinds of the issue. It's like when you're looking at it, it's like, where? I've got this, all I know is got a pop. Well, there could be any of the huge number of reasons why that pops. So here's the first rule. Don't use the debugger. Now, those of you who've watched me programming will know that I rarely use a debugger. I find that if it's something that's a static problem for which the debugger is suitable, I can probably debug most of it by looking at the code, especially if the code is, you know, well written. It's a little bit different when you go into C and C++. In C and C++, then you need to start doing extensive logging, especially if you have memory issues. When I was working in my C engine, this would happen from time to time, and the debugging process would be tedious. But it's not really helped by a debugger much. In general, the only thing that I find that a debugger is useful for is figuring out where the crash happened in C and C++. C#, I really don't need it, because I can handle it with logging. But the reason for not using a debugger when you've got some kind of dynamic thing that you're debugging is because you need to understand how things change over time, and the debugger is terrible at that. What's really good for that is to just log. You just print a log out over time, and you analyse the log, and in one go you can see how things move or change. You can even plot graphs, and this is a very valuable thing. So anyway, I'm not using a debugger because there are a huge number of techniques you can use, and so I'm going to just do the first one here that will come to mind. It's the simplification. Now, when I'm debugging, I don't make assumptions. So often I take steps. I'm thinking, well, what was the point of that? That's obvious. Well, you kind of learn that you never say that when you're debugging. So what I'm going to do is force the angle to always be 0. Now, this really, really simple idea, because now I have removed the whole of start angle, start time, all this other crap. I've just removed that out of the equation. And then what I'm literally going to be drawing every frame is simply 0, 0. So then I think, where do I expect the ball to appear? I would expect the ball to appear here, because in my coordinate system, this is x, positive axis. This is the z, y, positive going up. The cosine of 0 is 1. The sine of 0 is 0. 1, 0. It will put me about here. So you do the test. You hit play, and you look at what happens. And that was really weird, because it's kind of moving. And so then you go, hang on, that was impossible, until you realised you forgot to save the file. And then you try, and you try it again. And what do you get? That's it. And now you are in what I would call, I need a name for it, but you're not in La La Land. Let's put it that way. At this point, you know you're not in La La Land, because you know that what you have does what it should. It should put the ball there. The ball is there. Therefore, what you have there is good. And that tells us that this line is correct. Seems correct. Anyway. And why do you want to know that? Because what if you got it wrong? What if you'd accidentally swapped the sine and the cosine over? If you had the sine and you'd done this, assumptions. You might still see it move around, but now at this point we're looking at trying to nail down our coordinate system. You know, what happens if I had swapped those? It's in the wrong place now. And so this is why it's really critical to be meticulous, just like it is with mathematics itself, you know. So I'm going to continue in this vein. I've tested 0, and where would it be if I put it at 90 degrees? I think it would be north. Let's see. I don't have an automatic play set up here yet. But and now you go, no, Dino, that's wrong. You see, it's because I've done something else wrong now. It's like 90. Why is it 90? Because angle is in radians, Dino. So this is getting you some point. Okay. Oops. Let's keep at it until everything makes sense, because I moved one step forward and then I went into La La Land. Now let's see. That's debugging. Is you find a spot that isn't La La Land and you try to get to where you want to be without falling off into La La Land. So that is 90 degrees. That's what I would expect. Okay? If I put in 270 degrees here, so I think we can be quite confident now that that line is doing what it should do. So now, right, the problem was that the start angle was incorrect. So I'll tell you what I'm going to do. I'm going to put the start angle in and comment out the rest. So now it should be the start angle, and it was not going to move. It's just going to, when I hit play, it might change the distance, but I expect the angle to remain the same. Let's have a look. Yeah, I'm in La La Land. Why am I in La La Land? Because, once again, busy talking, I didn't save the file. Let's try that again. I can save the file. You hit play. And now you can see that it's popped. It starts off there, and it goes, boop. So this means that my code is broken. And they're just absolutely defined as broken. You can see that it's broken, and there's no point in progressing until I can find the angle that I need, so that when it places the ball at the starting point, it's at the right angle. That now is my focus, my 100% focus. I'm not even care about anything else. That I have to understand. And so you're going, why? So imagine that you've done that for a bit, but there isn't a lot to play with here. You know, it's like, what you got to play with? There's the position. You could check, you can draw lines. You say you're doing all of this, and you go, it's just like, where's the assumption? Always an assumption. It's not working because there's an assumption I'm making. Price overrun. So at some point, this happens. You feel compelled, actually I have a thing in my editor for this, you feel compelled to look up the ATAN2 function definition. So, returns the angle in radius whose tan is y over x. Rise overrun. Returns the angle whose radius whose tangent is y over x. This function takes account of the cases where x is 0. So it's not going to blow up. It's all a bit confusing, isn't it? Okay, so in theory, I get the... Look, I'm looking at the example code. Are you looking at the example code? I'm looking at the example. Are you looking at the example code? What's this example code got in it? Math F ATAN2 relative x relative z. They're doing exactly the same thing I did. I don't understand it. So more agonizing going on about this as you try to understand what's gone wrong. And you know what you have to do? You have to calm down and just reread it. So at some point, you learn to be very meticulous in the way you read manual pages. And that's the first lesson. The second lesson is, don't take example code for granted, because there's a possibility that the person who wrote the example code made the same mistake that you've just made. Public static float ATAN2, float y, float x. Oh, wait a minute, that's got to be a typo, hasn't it? I mean, that's clearly a typo. I mean, you know, you kind of look down here and you can see, look, here they said x, z. Well, I know it's z, but not y, but that's because they probably were doing the same thing that I was doing, with the x, z instead of x, y, thing. And so what do? You go and look up ATAN2 from somewhere else. JavaScript. Calculate angle degrees, x, y. Math ATAN2, y, x. Tum, tum, tum. The whole thing is because this is in fact correct. It is y. You need to put the y first and then the x. You said we drove my ex-colleague mad. But there is a reason for it. The reason is that it is the way the tan function works, because there is just the tan function itself. There's ATAN2, which works for the whole circle, but the tan function only works part of the circle, and what it returns is, well, you can see when you look at the tan function instead of ATAN2. Tangent of f, the angle in radius whose tangent is f, of course doesn't really help too much, but the way you measure the tangent is rise over run, that is y divided by x. and because of that, the tan2 function puts the y first and then the x second. It's a mathematical convention which can be terribly confusing. But there is a reason. The reason is that it makes sense mathematically. Oh, so what you do then is here you have to go here and you have to swap them. So okay, we'll go back and we try. Now, I just save the file. We are looking to see if we're in La La Land or not. Can we get out of La La Land? Let's have a look. And that looks good. Look at that. The position has shrunk. You know, the length, the distance from the origin has reduced, but the angle is correct. So, are we done? No. What we'll do is we'll test this by trying other examples out. We'll move it here and see how that goes. And now we're good. Yes. Lesson learned. Cool. Oh, my gosh. So, if that's correct, we'll put back the code that I had at the beginning. I'll put it back. All I have done from the beginning of the debugging session is swap the x and the z. And if I hit play now, play. Now that's an interesting thing. It got that right, but now I can see another problem, which is that kind of stutter at the beginning. Now, if you were watching last week, you'll have seen that the stutter at the beginning is due to Unity stalling right at the beginning when you hit play. So, in fact, this time thing gets set, and then Unity stalls, and then the thing pops. So what I'm going to do is to set this up like I did last time, so that you can actually see the motion without this stall right at the beginning, which is hugely irritating. And a way of doing that would be, I'm just thinking, what is a cheap way of doing that? We've got the start here. I'm going to create a function called begin, and this will begin the, I'll call it begin rotation. So, and for this I need to remember the start time when I began the rotation, and then I also want to know the start angle when I began the rotation. And then I probably want to know if I'm rotating or not. If it's a bit messy, but you know, whatever. What can you do? You know, we'll do bool rotating, which is obviously going to be false at the beginning. And then when we begin the rotation, we set the start time, we set the start angle, and we set rotating equal true. And then down here we can say if rotating, then we execute our code. How's that? Now we need to know when to begin rotation. I'm going to just for the what was it? Invoke. I think, wasn't it? We can do it that way. Invoke begin rotation 1 second. Yeah, except this requires a string. It's hideous, the invoke function, but I'm going to just use it for now. Right. P does not exist. Oh, yes, that is true. Let me put that in there as well. There we go. Hit play. And now, yeah, so 1 second after the start, which gives enough time for Unity to sort of start up, barely. And you can see it still pops right at the beginning in terms of distance. So, oh my God. This just gets more and more complicated, doesn't it? It's just like, wow. Distance. Radius, I'll call it actually. Radius is probably better. That's the radius. The radius is going to be set equal transform dot position dot magnitude, right? And then instead of multiplying by this 2, I multiply it by my radius. Now, the interesting thing about this whole story is that I used to draw circles on my acorn atom in BASIC, in assembler as well. An assembler? We're going to have fun when I show you another way of doing this. Anyway, there we go. And this is at least working. It starts off in the right place. And now, if I move this somewhere else, say here, and I hit play, and yeah, there was much rejoicing. Hurrah! What a mess. Where was I going to go from here? I've got sine and cosine and atan 2, and well, I suppose it gets the job done, doesn't it? Well, what about if we could do it without actually using any trigonometric functions? In fact, couldn't we do it without using angles at all? Well, of course you can. So I'm going to go and try that. I think we can say that this is functionally, though, correct. It's like, yeah, after 1 second, the thing starts rotating, given the particular position that it was at initially. That's what we have, and we have a solution, and that seems to work. Good evening, Raduga. Long time. How are you doing? Good to see you. I'm doing a maths workshop at the moment. We've got as far as drawing a circle, or rather getting an object to move in a circle, giving an initial point, given an initial point to start. I'm good, thanks. Because I really don't like this. It's got angles and everything in it. So what we'll do is I'll just go and say hash equals and copy this and going to go with a different approach completely. The first one is that we could just ignore all of this maths and just do the following, which is to say transform dot rotate 0, 1, 0. No, wait a minute. That's rotating. Yeah, you can see a little sparkling there. It's actually rotating the. It's rotating the ball. Oh, yeah. Okay. We didn't want to rotate the ball. What we wanted to do was rotate it around the center point. So we could do this rotate about function, if I remember rightly. we need to give it an angle and an axis. I'm going to just look this up on the Unity search. Rotate around, in fact. And it takes a point, an axis, and an angle. The point is going to be vector 3.0, so rotating around the origin. The axis is going to be vector 3.up. It's the y-axis that we're rotating around. And the angle is going to be just 1 for the minute, so it would be 1 degree per frame. We can do a test, and there we are. Now notice again, what I'm doing with my pattern here is I do what I call the, well, I don't call it anything, it's like the smallest testable thing that takes me in the path that I want to get to. So I just do this way out of habit, you know. So here I've done a rotate around, and I know if I do this, I know what I should see. And immediately I see an issue because it's actually rotating the wrong way. I wanted it to rotate the other way, counterclockwise. Because mathematics, it goes around this way. This is the other area of confusion, right? In mathematics, angles are measured from the positive x-axis. And so they go around, and they go around anti-clockwise. But we all like to think of things as going clockwise. And it's got to do with the way that the mathematics was put together, that goes back thousands of years from how they started measuring the circle. And they drew the circle out. They immediately thought about the x-axis, I guess, was just where it naturally started, the starting point on the circle, for which all the sine and cosine functions are defined. Because you could have the starting point being somewhere else on the circle, and you could have had it that they all go clockwise, but they don't. The sine and cosine functions describe a circle of radius 1 starting with a position along the x-axis, that's coordinates 1, 0, and moving in an anti-clockwise direction. That was the convention. And so it remains so mathematically. But that isn't what's happening here. You see, here, where Unity is using, it looks like clockwise. At least you think that it's clockwise, but in actual fact it is anti-clockwise. It's just that we're looking downwards. Because we're looking downwards on the axis, we're looking at the axis from the wrong way. Fascinating, isn't it? We're looking down. If we got underneath the ball and looked upwards, which we can do, like this, now we're looking up the y-axis, and in fact now it will be clockwise, anti-clockwise, which just goes to show. In fact, I'm kind of curious now, what would happen if I put in 0 here? Ah, but this is a rotate around. So yes, there isn't an absolute position. Fine. So there's that explanation. So what it means, if I want to stay consistent with the other method, then I need to make this negative. Or, no, I don't need to make it negative. I can just reverse what the axis is. The axis, make the axis point downwards because we're looking downwards. So if I reverse that, we should probably have it going, there we go. And now, because it's a pure rotation, it's already taking into account the initial position of the ball. I mean, you know, I can put it here, and so that just seems to work. And the only thing is that we're doing this, we're not taking into account the delta time anymore. So if we followed the same pattern as before, we'd still need to have a start time. And to get around the problem of the stall, want to perhaps put the rotating in, so I'm going to just do the same thing here. Void invoke begin rotation. The update is going to say if rotating and begin rotation actually probably doesn't need. Oh, I don't need the start time yet. No, that doesn't. Well, I want to put that in somehow, but I'll need a bit of thought. So what I'm going to do is just go this rotating equal true, and so now it will start rotating 1 second. Because the thing to remember here is that there is state now. It's actually using the object's own rotation as the state. That every time it rotates it a little bit. But that should work. If I push this somewhere else, I get once this little pause and then boom. This is certainly a lot simpler than what I had here. But on the other hand, it's doing everything itself. So you're not going to learn about the mathematics by using this rotate around. And most of the time, people just use that without thinking about whether there'd be an advantage to sort of looking a little bit under the hood. One of the effects that you get from this is that you tend to get patterns, especially people copying code. And I've seen these, they're almost like coding memes, or they're fragments, and they kind of grow, they have a life of their own. So that in the end, you can end up with a clump of code that could actually be one line, but is in fact 5 or 6, because it's just something that has replicated itself, copy and pasted in different by different programmers, and sort of had little bits get attached to it. It's a bit like a virus, you know. It's like so. Because as again, you know, what I'm showing here is not the point here. Is not the it's not the issue of I want to rotate an object around. In the end, I'd probably, especially in prototyping, just do it this way in practice. This is not about in practice. This is about in theory, right? So the one thing that this doesn't have, that this had, is that this is stateful and this was stateless. So if I wanted to make it stateless, then I wouldn't be able to use the rotate around. I would need to have a calculate a rotation and apply it. I'm going to try and do that. That will be in another method here, because this is something that, you know, is also, I think, valuable. So the next version of this is one that is stateless. And by that I mean I just set the rotation at every frame. So I can't use this rotate around anymore. What I have to do is just figure out rotation equals something. What's it going to equal? Well, if I follow the same pattern that I had down here, I want the start time. Right? And then, do I need a radius? Actually don't, because the radius is held. Well, yeah, interesting. Do I need a radius? Actually, I do need a radius, because I want to do a rotation relative to a certain point. I can't use the trick of the rotate around. So what I'm going to have to do, I think, is also hold the radius. So I'm going to need that. And then, will I need the length? No, that is the radius, right. Do I need the start angle? Yeah, I'm going to need the start angle. So in fact, I end up needing the same stuff. But what I'm going to do is not use sine and cosine. I probably need to use the atan too, because I need to set up the start angle. So I'm going to do that. I set up the start angle, I say it's rotating, and then here there's some expression that I can get that would do this properly. Problem being is I need to set rotation around a particular point. And in order to rotate that, I need to translate the object. Oh, hang on. I need to take the vector and then rotate it. I need to rotate a vector so that I have the start angle. And so what I'm going to do, because there's a few things I have to hold in my head here right now, what I'm going to do is just write them out as, lines of code, so that even if it's not the most efficient code, you can optimize it afterwards when it works, right? So what I'm going to do is start off with vector 3, 0 direction, for want of calling it something. And this is going to be new vector 3, and it's going to lie along the x-axis, which is fine because that's where we start. This is the vector that represents 0 degrees. That's basically what I'm doing. I want to create a vector that represents 0 degrees. For that, I need to take my radius. This vector, radius 0, 0. That's the 0 direction. When I begin the rotation, I'm going to need to also capture the current radius. So there we go. You transform rotation is going to equal a, because it can do the rotation. That doesn't help me, you see. I can't, because this is the rotation of the ball. Which brings me to another point as well, is when I do the rotate around here, I'm also rotating the ball at a subtle point. Maybe you don't want the ball to rotate. Certainly here, the ball's not rotating. That could be annoying if you don't want the ball to rotate here. But here, I can't set this because that's just going to set the rotation of the ball. I suppose I could make a parent object and then rotate that. And that is the solution a lot of people would use. They would just say, rotate the parent object. But, that's not very mathematical-y, is it, really? So, and then you create another object in the scene, and there's another thing to go wrong, and I don't know. Anyway, on transform rotation, can't use that. I need to set its position. So it becomes this, actually. Position is equal the 0 direction vector rotated by a certain number of degrees. And since it's a vector, to rotate the vector, I need to use a quaternion. So, because a quaternion is basically Unity's way of representing the rotation of a 3D object in 3D, not just Unity's, but that's basically what it is. When you have a rotation, the rotations are defined in quaternions. So I need to have a quaternion, and you can do a quaternion Euler 0 and a rotation around the y-axis. So that is going to be with this, which is now in degrees. So that is this whole bit here without the degrees to radians, because the quaternion function takes degrees, not radians. So basically what I'm saying is I measure the amount of time from the start time and then multiply it by the number of degrees per second, and then add that to the start angle and use that rotation to rotate the initial vector, which is the one lying around the x-axis. And this, in theory, should work. We'll try it. We'll try it and see what happens. Does it compile? No. What did I do wrong? Oh, it's this typical thing here. I have this thing. Confused at the time. Let's try this again. And position, because transform dot position I need to do. Hey, Music Links, how you doing? Good to see you. And I've still got a problem. transform position equals quaternion no, because you can't make it, you can't assign a quaternion to a, you cannot assign a quaternion to a vector. What I meant to do was rotate 0 direction. I do that by multiplying, let's see it better like this. You take the rotation and multiply the vector. It's kind of a bit reversed from what you're thinking. You apply the rotation to a vector by specifying the rotation first and then multiplying the vector. In effect, you would understand it more easily if there was a function called rotate vector that took the vector and applied the rotation, applied the quaternion to rotate it. But frankly, you know, this is using operator overloading in Unity, so basically this multiply does that. It's not a real multiply. So it's transforming 0 direction by this rotation, which is a rotation in the y-axis in degrees, defined as the start angle plus the amount of time since the start, multiplied by 60 to get 60 degrees per second. All right, let's try that and see if that compiles. That does compile. Now, what happens when we run it? Well, it almost worked. It's just interesting that it's gone and... Oh, yes, of course, because I need to make sure that my Euler angle is negative for the reason that we've just said. Hi, Massacre. We may have a return of Howl eventually. Oh, what's happened there? Cannot be applied to type float int. Why? What happened? Oh. Parenthesis in the wrong place. There it is. Now we hit play, and maybe this time. There's a jump. That jump at the beginning, that's annoying. Why did it jump? Begin the rotation after 5 seconds. Yeah, it's not. Oh, because I've not set the start time. Yeah. There we go. We set the start time. Music and performing arts. Well, that's it. Mathematics is art. Matey. Hi, Micon. How you doing? Oh, yeah. Oh, jeez. Okay, hang on. Broadcast options. Mathematics. Maths. Math workshop. There we go. I seem to have an echo. There's the echo's gone. So what we need to do now is yeah, actually, so I have to reverse. I'm making it go the other way, right, for the aforementioned reasons that I was saying before. Come on, you can do it. Oh, it almost worked. It's because it's 5. I could have changed it to 5 seconds, which just feels like a net forever. Okay, that doesn't seem quite right. Almost working. No, it reset back to 0. So we've got to figure out why. That's because the start angle doesn't seem to have taken. It's not taking into account the start angle. That's most disappointing. So what I'm going to do is split this out, makes debugging a little bit easier. If I say float angle, yeah, I abandoned the whole of the C, well, shelved the whole of the C thing. I ran out of steam, but it served its purpose. I enjoyed it. It wasn't about making the game. It was about the process. It's like, about the worst thing, the most unappetizing thing I can think of is to independently develop a video game with the hope of selling it. I'm just so over that. It's just like, here's a game. I made a game. Anybody want to see my game? It's like, it's like, jeez, go on, please. I'd pay you to play it. You know, it's like, so why is it doing this? So I'm trying to figure out now is why it pops at the beginning, and it shouldn't, because I included the start angle in here. Wow. So again, now using the technique of hardwiring in order to see, because I don't understand what's going on, and for that what I'm going to do is look at what happens if I force the angle to be 0. And that is correct. If I force the angle to be 90, because it is in degrees now, not radians anymore. Oh, it means the start angle. Oh, wait a minute. Yeah, hang on. Start angles is actually in radians. This is in that's why. It's like 1 radian is about 60 degrees. And if it's 1, it's going to seem like it's practically 0, isn't it? So, angle always gets you that one. Angle degrees equals start angle radians. I'm going to write this explicitly out. So there's that start angle in degrees equals that. Right, is all of this, I can multiply it by math f dot hang on a minute, because this 60 is in degrees. Start angle, okay. Then probably the more correct way of doing this is to take the start angle in radians and multiply it by math f radians to degrees. So then this is in radians, and this is now in degrees, and this is in degrees. And yeah, it would be great if C# had strict type checking. The name angle does not exist. I can get rid of that. I think that's actually good now. Let's see. Okay. No. Let's try that again. All right. And now we're out of La La Land. We're back on good ground, and there's another way of drawing the circle, or making the thing move in a circle, I should say. And this is working fine. So this version of it, which is in a way a bit messy, because I have to use the API of Unity, which uses degrees. And then I was using the a tan 2 function to get the degrees, to get the get it in radians rather than the angle in radians. There is, I think, a unity function for getting the angle of a vector. I'm going to actually see now, as I'm curious. Get angle of vector in unity. Vector 3 angle. It does between two vectors, the angle between two vectors. And as a result, it's going to always return the shortest of the two angles. I don't want that, do I? It's like, is it ever going to be negative? The result is never greater than 100 degrees. But that means that, are they ever negative? No, it doesn't say that. So it's actually, this function is useless for me because I want to know the angle. You know, this is different to this. So you would hope that Unity would have provided, since they love their degrees, you'd think they would have provided some way of getting the equivalent of the a tan 2 function in degrees. Hey there, FME, how you doing? Good to see you. No, I don't think you can move the pivot point of an object in code. It's something that would be quite nice if you could, but what you have to do is parent the objects. You have to make it a child of another object, and then you can, in effect, do it. It's a bit annoying. So what I want to know is a equivalent of a tan 2 in degrees unity. Yeah, there's the a tan 2. This is Unity code here from 2015. You know, this is great when you're looking at different code. It's like find degree given x and y. Well, those are taking integers. Why are you taking integers? And then it uses the a tan 2 function. And notice it says x and y. It should actually be yx. It's had 7 upvotes. It's the best answer. Yeah. Let's have a look at this best answer a minute. Because seriously, I am so annoyed with all of these resources. Because it seems great, doesn't it? It's like we've got crowd resourcing here. You know, everybody can contribute, your community, and when you get things like this, it's just, you know, it's just variations on how certain people, I won't mention, manage to get to run superpowers. You know, it's like, it's mind-blowing. I mean, first of all, find degree is taking integers. Why the hell is it taking integers? You might as well take floats. I don't know. Take a float value, and it's taking the mathf function, and it's casting it to a float. Why does it cast it to a float? There's no need, because this function already returns a float. Mathf returns a float. The a tan 2 function returns a float. Why do you need to? Why? Why? A tan 2 xy. It's not xy. It's yx. Divided by pi, multiplied by 180. Why not use the rad2 degree function? If the value is less than 0, add 360 to it. Why? Why? Oh, because you want it to be between 0 and 3. Sure. Maybe I'll let you have that one. Maybe. I mean, I'm still a little suspicious about edge cases. What if it's 0? Oh, then it's 0. That's fine. What if it's exactly 360 degrees? I don't know. But this is covered in here with the conversion constants, and then, you know, the two. Here is a slightly. He's used the math to degree, and then it's copied. No, I don't know. Whatever. Anyway, enough of that. Well, FME, because I've given up, and because I've given up even trying, they don't need to try anymore. You know, I feel sad for people that, you know, would like to actually have sort of better football games out there, and all the rest of it. But just, and now I'm in the same position. I feel just as sad. I feel sad for the fact that you want to bash your head in after you were trying to play FIFA and Pro Evolution Soccer. It makes me sad. But what can you do? And I'm also sad about global warming, about the destruction of the environment, about my main thing at the moment, though, is politics. How is it that people who don't know what they're doing always get to be in charge? Well, it's not always. But in my experience, it's like it's rare, it's difficult, it's really, really difficult to find someone who knows what they're doing, who's in charge. It happens from time to time. I kind of spend my time going around looking for such events. You know, it's a rare thing that Venn diagram has power, is competent. You know, that it's like. Anyway, I digress. Severely, yeah. These aren't the philosopher kings Plato envisioned. Hi, Will Watley, how you doing? No, in fact, philosophy just died as well. They missed the point of philosophy. Philosophy is not about trying to square things away. Philosophy is like a dance. It's like a performing art. Anyway, a bit like this. what I have here, right, is what I'm going to do is show you. It was the whole point of this exercise, really, was to show you something. I don't want to run out of time. Yes, I think so. It's what? Oh, will I ever get back to creating a football game? I don't know. I can't. I don't know. I'm having more fun creating my radio station. It's to do with music. Hardly anybody listens to it, but that might change because I've only just started it. You know, but what's nice about it is that you just get on and you just do it, and in a way, I quite like the fact that there's very little feedback, because I don't really want feedback. So it's actually interesting. It's like if you're an author, if you go back in time before the internet, you'd write a book, and maybe you'd receive some fan mail. But by and large, you can just let it do its thing, you know. If I am very tempted to write political independent type. But you see, that's the thing, not to sell, but to make a point. Anyway, back to the topic in hand. What I'm going to do now is show you a very old way of drawing a circle, because it's interesting. So I'm going to start again. I know I have a position. I'm going to keep in the rotating thing because this is the workaround for Unity's annoying habit. So I do the invoke after 1 second. No, it's not. Well, Bressingham's algorithm is actually interesting. Believe it or not, I used a 3-dimensional Bressingham's algorithm for a grid-based spatial database for optimizing ray collisions on geometry. And so it's basically, if you use like an octree, well, it wasn't even an octree, it was a grid. It was a 3-dimensional grid, you know, it's a cube thing. You break the whole of the 3D world into cubes. And then for each cube, you have a list of the different objects in it. And when you cast the ray, you need to search those cubes. But you need to create a list of cubes to search. And so to create a list of cubes to search, I used a 3-dimensional Bressingham's algorithm to draw a 3-dimensional line through all the cubes to know the cubes to search. That was fun. But the point here is that, you know, even old algorithms like Bressingham's algorithms that you know, you won't get taught in modern computer science, you really should. You using Bressingham's circle with Bressingham's line drawing to produce, yay, yay, Mycon, yay, oh man, I love that. You know, I'd love to know more about it. Maybe you could do, you could stream that. That sounds quite interesting. I love it. All right, so what I'm going to do is begin the rotation. Basically, what makes me happy is when people aren't just regurgitating the same old thing and they're actually trying, and also respecting the work of our elders, because there's wisdom in there. We just miss a lot of the time. Social media doesn't help at all. So, if rotating, so this little bit here is just going to, after 1 second, it's going to start calling this code in here. And now, what I'm going to do is make my ball move in this way. So the actual code that I'm going to write to make it do that, I'm writing here, in this little part here, right there. And I'm just going to do it without saying anything and see if I get it right first time. One caveat, it would need calibration in order to get it to be the same speed as the ball that's there. I don't care about that for the minute, I just want to try it out. So what we do is we say vector3 p equal transform.position. Now this is in fact, just to highlight the point, this is not the mathy bit. And transform.position equal p. Okay, right. That's not the mathy bit. This is the mathy bit in there, right in here, in this bit. Okay, this is the bit that does the actual. Right. Okay. So what we do is we do p.x plus equal p.y divided by 16. P dot y minus equal P dot x divided by 16. It worked, but I forgot to make it a Z. Let's try that again. Oh, let's try that again. Oh, right. Oh, no, Z. I'm sorry, I made a mistake fixing that. Okay, try again. Right, drum roll. Are you impressed yet? There's 2 lines of code I managed to do the whole fracking thing. Makes you think, huh? So what this is a very old trick. It's a really old trick which would allow you to draw circles really fast on very old hardware, even if you didn't have floating point. Toasters? What do you... Hang on. Well, everything... Just seeing what Icon's saying, but everything that gets done these days, software-wise, is a lot worse than what they did back in the day. Software used to respond immediately with those archaic computers. Nowadays, computers are supposed to be fast, but we end up waiting for the software. Yeah, it is absolutely incredibly tedious. I mean, I don't know. I've probably got a smart TV. You just go on your smart TV. Amazon Prime, look here. You push on the controller. One. Boom. It's like the lag on those things. It's terrible, and nobody builds UI properly anymore. There were rules that you would follow to build rules I know because I was there when they were invented, but they've all been forgotten. So not only is there a lot of lag, but there's no visual indication either because it's too difficult, because programmers can't do that kind of programming anymore. They just can't. The skills aren't there, and that's why. I've got this radio, right? I wanted to get an internet radio to try out with my internet radio station. The most appalling user interface design ever. The whole thing, I've spent hours trying to do the simplest thing with this. We are suffering from a software crisis which is so horrific, people don't even know. It's only if you've been around a while and you remember how things were, and you can compare it with how things were back in the old days on hardware that was a lot less powerful, but yet was more responsive, is because the quality of software and user interface design has fallen so badly that the tech can't keep up with it anymore, and our computers are getting slower and slower. And I just spent the last couple of days just pulling my hair out on this and saying, yeah, we need a solution. We need a solution. Something that keeps going through my mind is we need to have certified programmers. I've just had enough. I've had enough of the fact that we're running around all these people who call themselves programmers who really don't know how to program. When you're interviewing people to work in video games and they can't tell you what the dot product is. And just like, what's happened? It's tragic. And the thing is, you are actually seeing it tangibly in the devices that you use every day now. They're getting slower and less slick. There's no doubt about it. Yeah, I kind of know what you meant. I mean, it's like progress bars. Yes, progress bars are actually quite difficult. Yeah, too much. Too much. It's not agile so much. It's just there's too much focus on. There's too little focus on programming. There's too little programming going on. And Brunos, I've got some bad news because this is of apocalyptic nature. Because if we don't actually generate or create programmers who know how to program properly, if they all disappear, we won't be able to maintain our infrastructure. We just won't. And if you're a hardware engineer, it feels like you have to really get your certification for it, you know. But software developers, they just get away with it. They're just sloppiness. I can't understand how a company like this is like the pure people, you know, whatever. All the work that went into designing this, and it's a physical product, so you actually got to build the damn thing. And everything's built. This is difficult to build hardware. You know, there it is, all done, all that effort made to build the hardware, and they put the software inside in the hands of people who barely understand their jobs. I know it sounds very harsh, but you know, no one needs to take it personally because this is everywhere. If you think I'm being unfair, tell me. Well, I really don't think I'm being unfair, so I think it's something that needs to be fixed. So that's one of the reasons why I like to do what I do here, is try to explain stuff like this. This trick here for drawing a circle, nobody knows about it anymore. In fact, it was listed. The origin of it, and there's more about it that's quite interesting. But the origin of this is, I think, not known precisely. But you may know Jim Glynn. Now, Jim Glynn has retired, but he was a graphics engineer, programmer, and he has a shader technique named after him. In fact, the Blinn Fong shader, for example, is the Blinn is him. It's just a lighting model, a way of, you know, reflecting light in a shader, or not reflecting it, but, you know, you need to bounce off whatever lighting model. So, but he had this Jim Blinn's Corner thing, and in there was one particular article. There's a book that you can get, hideously expensive, of course, because we don't want people to have easy access to these gems, do we? But he lists a very large number of circle drawing algorithms, and this particular one is covered. But that isn't where I first encountered it. I first encountered it in the Acorn Atom manual. So the Acorn Atom computer that I got around 1980, and this technique for drawing a circle is actually listed there. You'll notice, to get back onto topic, that this circle is stable. Have you noticed that? It hasn't grown in size and it hasn't diminished in size, and this is connected a little bit with the exercise that, you know, I was showing you last week. We're trying to make something bounce in a stable way so that its height didn't get higher or lower. And okay, how is this working? Before I go into how it's working, I want to point out one other thing. You'll see on here that I've got this divide by 16. Why 16? Well, in fact, it can be anything. If I make it bigger, I make it, the slower the rotation. So in order to adjust the speed of rotation, you would need to figure out the correct value for this, which isn't actually that difficult. What is going on, though, is that it's actually rotating a two-dimensional vector using a rotation matrix. It's an approximate rotation matrix. You see, if you've got, I try and mark it down with, like this. If you want to rotate a vector in 2D, this is a little bit of linear algebra here. To rotate a vector, you need to define your rotation using two vectors. So you could have xx, xy, and then yx and yy. Now, if that was, actually, I can draw it out like this. So this is a matrix, a 2x2 matrix. Let me make a comma in there. And what you would do is you multiply that by a vector. So we could call this just sort of x and y. And this will allow you to rotate. If you multiply these together, it will allow you to rotate them. It becomes x, the actual result. So I suppose I can put the little thing in here. If I do this, what you end up with is a new vector, and the vector is xx times x plus xy times y. I want to point out what I'm showing you here is actually elementary linear algebra. So it's the kinds of stuff you get taught in A-level maths, even before university, maybe even before A-level maths. I can tell you right now that if I use as a filter for hiring people whether or not they could explain something like this, is anyway, yx times x. It really shouldn't be this way, you know. Y times y. So this is basically how rotation happens. I mean, in 3D rotations, it's the same, except you have a 3×3 matrix and you rotate a 3-dimensional vector. But in principle, it does the same. So what this means then is that you can rotate any vector in 2D by simply using 4 numbers. So if you want to rotate by an angle, it becomes something like, I might get the signs wrong, the angle is A, does that make sense? Because what's happening is that you're creating 2 unit vectors that are slightly rotated, and you're using that to rotate another vector by that small angle. Now here's the thing, if you want to make an object like this rotate, you can use a small angle. So let's make the angle really small. The thing is that as you make the angle small, you find that the cosines get big and the sines get small. So you'll get something like approximately some value, which I call R, approximately our rotation, approximately 0. Well, actually, it's not, it is R. Well, depends which way you look at it. I'll just put it like that. And then the second one here is approximately 0. And approximately R. Now, I may have got the signs wrong. I'm just having a look at this. So this becomes 0x sine y. Cosine. So the cosine times the x and the sine times the y. It's actually, I don't like that. I'm going to change this around. It's just because I can see that wasn't going to work. So I do cosine, sine, cosine, and cosine, sine. The only thing that this affects is like which way round we're going in the coordinate system. But if I do that, basically it means that if A is very small, the sine of A is practically 0. So I'll just write down the approximation like this. And what you get is that the rotation is the cosine of A times y, and the other side minus the cosine of A times x. Because those disappear, so you actually get cosine A. And it, don't hold me 100% to the accuracy of the signs, or whether I've got cosine or sine or whatever. It's not the point. The point is the principle, so you can see where it comes from. And if you look carefully up here, okay, well, I just clarity, because I have Z instead of sorry, it would be like that. You can see how it's a constant multiplied by the Z. In fact, if the angle is very small, you can sort of divide it down. This is in principle, okay? I'm going to just get rid of that because I can see already that that's a little bit wrong. But the point is that you've got a rotation that for small angles, you can forget one side and make it an approximation. Now, the funny thing is, and that's what this applies, and the thing is that if you're doing this in assembler or on very old hardware that didn't have even floating point, you could achieve this shift. You could achieve this division by shifting the bits. So you could do that. That would be a divide by 16, which is why I said the 16 originally. You would use integers and maybe fixed points. You'd scale them up and scale them down, whatever. Anyway, the point is, as a result, you get this. But the thing is, it's an approximation. So really, you wonder why is it that it doesn't, that it remains stable. So again, let's say, I say again because it was we tried something like this last week. You may notice when you look at this that there's a bug, or at least what looks like a bug. Because what I do is I modify x first, and then when I modify x, I am actually in the second line applying the modified x. Alright, this is, a mathematician would look at that and go, ooh. Alright, let's fix that bug. So to fix the bug, what I would do is go float here, let's say nx equals p dot x plus pz divided by 100. Okay, and then my new y equals new z, sorry, equals p dot z minus px divided by 100. And then over here, well, I'll keep that on. So now what I can do here is say p dot x equals the new x and p dot z equals the new z. So what I'm doing is I'm making sure that both of these calculations work on the previous values of x and z, px and pz, instead of doing what I did here, which is kind of a classic bug when processing these things. It's the kind of mistake that's often made. You'll notice that it worked without the mistake, and worked with the mistake. This is actually quite interesting. So what if I try running this? What do we have now? So we're going to run. It should probably say it's running in a circle. Okay, I'm going to make that circle a lot faster. So this is in effect changing the angle. I'm making the angle bigger, right? That for each step. So by making it bigger, though, the error that is caused by the assumption that one of those values is, it wasn't the 0, it was actually nearly 1, it was the cosine. So in fact, I had it right way around the first term. Anyway, the thing is that the bigger the angle, the more skewed this becomes, the more the approximation is worse, yeah, because it's best for small angles. So if I'm making the angle bigger, it should sort of exacerbate any kind of problem that you get from this. Let's have a look. Oh, maybe I need to actually save it. So let's save it. Oh, we've got a problem here. Okay, that came out really fast. is spiraling. And the reason it's spiraling is because, yes, it's an approximation. So in fact, you're getting what you would expect to have happen. Because it's a skewed rotation, because it's an approximation. But this approximation was fantastic when you were working on not very powerful hardware. So it would allow, even on early 8-bit computers, you could have all kinds of rotation. There was a game on the BBC Micro called Starship Command, I think, and your ship was in the centre of the screen, and all the other ships, starfields and everything, would all rotate. This is 8-bit machining. And everything was rotating. And it's quite clear that the way that this was done was by using this kind of approximation. It's the same technique that I used in this, which here will come up here, Adventure. A few years ago, Adventure Vision demo. So this was, the Adventure Vision is a very, very old console. A very old console indeed. It was made with 40 LEDs and a spinning mirror. All right, and I worked with these guys on this one, which was a lot of fun. And contributions, I'll post this so you can have a look at it yourself. There's the Starfield, there's classic Starfield, I did that, Starfield. But what I want you to see is that in a minute, the old Starfield, and this is on an 8-bit sort of, it's practically a PIC processor. Look, there is, the rope is spinning. So this spinning Starfield is actually done using the same algorithm that I've just shown you to get that spin. You make it spin the other way. So this is of course written in assembler. I had never programmed on this particular chip before. It's a lot of fun. You should try it again. And they do some great effects. There's all this other kind of stuff going on here. It's like, I'm not sure how they did it. And yeah, that's kind of weird. But I'm not done with the rotation. Sorry, it should be, here it is. So and then we've got, okay, and now it's rotating. And that rotation is being, this is Brescian's algorithm to draw the lines, and the points it's drawing between are being spun by using a squashed version of, just squashed vertically to create foreshortening of the points using the same technique that I've just shown you. So I actually reuse that. The same code that is rotating the cube here is the same as the code that was rotating the Starfield as well. So you'll have to fit it into very little space. And so if you haven't had that enough, then, you know, well, there we are. So there we've almost got a lead. That was a lot of fun. Again, it's the same thing. It's just been by using the same algorithm. So anyway, there we are. But this doesn't answer the question then. What was happening? Because this is going out of control. This is not stable. Well, it turns out that if you have this bug, But I just, you know, this thing where you apply the second transformation, or the transformation of the z coordinate, by using the x that you already modified first. The end result is a correction of the error, which is just mind-blowing. It still makes me laugh when I think about it now. Is that basically, if you do the approximation by introducing the classic error of, you know, applying a change to the first coordinate to the second, by coincidence, causes cancellation of the error, and so it actually fixes it. So it's a case of a bug that actually fixes. And it always makes me laugh. And it's amazing how stable it is. It just is. And it doesn't drift or anything. And I can show you that if I come and sort of like really. We had the 8. Let's go to 4. It's not going to be so circular, but it will be stable. Look how beautiful that is. You can see it's not, you can see very clearly that it's no longer circular. But the nature of it is that you can very efficiently draw a circle that's more accurate than your eye can tell. Hey Xavius, how you doing? Ah, thank you. So, I suppose the point I wanted to make is, with this, that I've been through a few different ways of drawing, not drawing so much, I'm making this point move around in a circle. And I wanted to make it that it would do that from a given starting point. And you try to do it using, the general tools that you have, or the way that you think about doing it. Starting out with angles. Then I tried it by using Unity's API. Then I tried doing it by using quaternions and actually creating a rotation. This was so that I could have a functional version, because this is holding state. It is quite quick, but the state is being held inside the object. And so, and this also had the effect of rotating the object itself. So I was looking at, let's see if we can get rid of that and avoid accumulating floating point errors. That became a bit more complicated because I'm having to sort of set the position manually by rotating a reference vector by the number of degrees every frame. But then we go back to the oldest technique that I know, and it's just has an elegance to it which is just beyond compare, frankly. And okay, it's an approximation. If you want it to not be an approximation, you can just make it a little bit more complicated, because what you do is you actually put in the sine and cosine terms in here. And so even that, if you pre-calculated the sine and cosine, yeah, you are in effect then doing a rotation by rotating a 2D vector by using a 2x2 matrix. And you hardwire the matrix, and it's very fast and accurate, and you don't even need the trick, because we've got floating point. It's perfectly fine. That is very fast, but I think it's also good to know about this other trick. It's also because it's quite amazing, really, I think, even now. And if you ever find yourself needing to, because you're trying to do a demo on the Adventure Vision or whatever, you're going to try and draw a circle, or you're asked in an interview, how do you draw a circle if you haven't got floating point? Fast. You'll know the answer now, won't you? Maybe if you brush up on the fixed point maths. So there we go. I'm Xavier. So good to see you. I am doing a math workshop, which I'm just about bringing to an end here. And it was about making circles making rotating objects. I wonder if that, but looking at different ways of doing it. So I wonder if that BBC micro game, if I can find it. Was it Starship? Starship Command, I think it was called. BBC Micro YouTube. It was a beautiful game. I really loved this. Oh, this guy. He's always there. We increased our sales by 2,547.395%. This Starship Command. It's a beautiful, beautiful game. I mean, really, I remember playing it. It's like, just, it's in front of me there. It's amazing. Come on, are you going to play, or is this just... Oh, sorry, it's because it wasn't playing. Okay, hit play. Yeah, watch this. This is an 8-bit, 2 megahertz CPU. Around 1982, I think. This isn't accelerated. This is the real thing. This is just. How could you not love this? So there you go. That is not something that you can do on 1 megahertz, a 2 megahertz 6502 8-bit processor with total RAM available of 20K after you used up the rest for your graphics. When you look at how many objects there are moving around on that screen, maybe there is a truth to what I'm saying about how the art of programming is not getting better, but getting ever worse. So anyway, at least you might have some idea now how to make these things actually rotate. So look at that. And so while this is going, it's also got that it also had that thing, you know, sparkling away when the communication's lost. Like super star controls. Hey Zagu, how you doing? Good to see you. Star Control Super Melee. I'll take a look at that. What was this from? 92. So this was a long time ago. Yeah, it's a bit, but you know, this is 10 years later, right? That's 10 years old. Okay. Anyway, I hope you enjoyed that stream, and so. Yeah, I'm doing this on a Monday night at 9 PM. The other scheduled show that I've got is Friday night, Random Jazz from 8 PM. And I'm hoping to do some more shows schedule more shows, but those are just the two that I'm doing right now. The other thing that is going on, which I'm going to give a plug to, is my radio station, which is radion.com, and it's still ramping up at the moment. We've got a PRS and a PPL license, so there are a lot of music on there already, which we are playing legally. But we're working towards actually having scheduled shows on there. At the moment, it's just there's just a playlist which we're extending the number of tunes on it. But the first show is due this Friday, in fact, at 7 p.m. and it's Karina's show, and she's got an hour of funk for us, so that's exciting. We'll have that. This yes, the what you have there, I don't know. That link, I'm going to check it, but I would go to the link I gave you because it's the actual website. Yeah, Radio Radion. It is that, but if you go to connection not private, yeah, that's the problem. Is that because I think it complains about that. I need to fix that. Just drop the H. Yeah. Ah. Okay. Yeah, you're right. Okay. That makes perfect sense. I'll watch out for that when I'm posting the link. But anyway, there we go. So yeah, well, we will. MyCon is fantastic. Yes, absolutely. I will figure that out. But anyway, I'm building it up. I'm building a whole SQL driven auto DJ system that is intelligent enough to periodically put in jingles, but will also be able to schedule the automatic songs when a show is coming up to fit into the available time and stuff like that. So it's quite an interesting hobby, that one. And maybe I'll do maybe that's subject of a workshop at some point. I don't know. Anyway, take care, everybody. Thanks for watching, and yeah, especially in this situation, hang in there. This has to end. I think we will appreciate what is important in life a little more when we come out the end of this. I know it's a bad thing. There's a lot that's terrible about what's going on, but there is also, I think, something to be gained from it, especially what I just said. Anyway, I'm off. Take care, everyone. Good night.